Hello everyone, let's discuss polynomials. First, let's define monomials. A monomial in x with coefficients in R is an expression of the form ax to the n for some n in the natural numbers with a in R and a not equal to 0. We say that the monomial a times x to the n has degree n and that the coefficient of x to the n is a. If n equals 1 or 0, then we just write ax or a instead of ax to the 1 or ax to the 0. Now, let's state addition and multiplication of monomials. The monomials of degree n, together with 0, form an abelian group under the operation ax to the n plus bx to the n is equal to a plus b x to the n. We introduce a multiplication rule. If ax to the m and bx to the n are two monomials of degree m and n respectively, then we define the multiplication using the rule ax to the m times bx to the n is equal to abx to the m plus n. Next, let's define a polynomial. A polynomial in x with coefficient in R is a finite sum of monomials in x with coefficients in R. We denote the set of all such polynomials by R square brackets x. The degree of a non-zero polynomial p of x in R brackets x is defined to be the largest degree of a monomial which is a summand of p of x. If the degree of p of x equals 0, or if p of x equals 0, then we say that p of x is a constant polynomial. Note that our definition of polynomials includes the zero polynomial, as 0 is the sum of no polynomials. The degree of a zero polynomial is undefined. As a polynomial is a finite sum of monomials, the sum of two polynomials is another polynomial. We can use distributivity together with a multiplication rule for monomials to define multiplication for polynomials. In this way, R square brackets x becomes a ring, the ring of polynomials in x with coefficients in R. Then, let's talk about notation for polynomials. We can write polynomials from R square brackets x using the notation the infinite sum from I equals 0 to infinity of a sub I x to the I, where a sub I is in R and a sub I does not equal 0 for only a finite number of values of I. So if p of x equals a n x to the n all the way up to a naught and is a polynomial of degree n, then we write p of x is equal to the sum from I equals 0 to infinity of a sub I x to the power of I, where a sub j is equal to 0 for all j greater than n. Following on, let's mention formal polynomial addition and multiplication. Suppose p of x is equal to the sum from I equals 0 to infinity of a sub I x to the I, and q of x is equal to the sum from j equals 0 to infinity of b sub j x to the j, and our polynomials in R square brackets x. Then p of x plus q of x is equal to the sum from k equals 0 to infinity of c sub k x to the k, which is in R to the x, where c sub k is equal to a sub k plus b sub k. Also, p of x times q of x is equal to the sum from k equals 0 to infinity of d sub k x to the k, which is in R square brackets x, where d sub k is equal to the sum from r equals 0 to k of a sub r times b sub k minus r. Now, let's make a remark about how to think about these polynomials. People usually meet polynomials first as examples of functions from the real numbers to the real numbers, but thinking of polynomials as functions can be dangerous over an arbitrary ring. For example, x and x squared are different polynomials in f sub 2 square brackets x, but they define the same functions f sub 2 to f sub 2. Next, let's discuss some results for commutative rings. Let R be a commutative ring, then R square brackets x is a commutative ring. Also, the set of all constant polynomials, ax to the 0, where a is in R, is a subring of R square brackets x, which is isomorphic to R. Further, if R is an integral domain, then for any f and g in R square brackets x without 0, the degree of f times g is equal to the degree of f plus the degree of g. So what is that? If R is an integral domain, then R square brackets x is an integral domain. And as ever, thank you for watching.